We are now going to look at mathematical proofs. You don't need to write these down, but here are some important definitions. A mathematical proof is a series of logical steps that shows that one side of a mathematical statement is equivalent to the other side for all values of the variable. And if it is always true, this is an identity. Cognity kind of emphasizes this more than you might see it in other places, but it is important to pick up here. There are different kinds of proofs, deductive, inductive, by contradiction, and today we're going to look at these algebraic proofs, deductive ones, left-hand side, right-hand side, and then in the next days we'll look at contradiction, counterexample, and induction. So for now, we're going to just try to transform one side into the other side. You can't move terms from one side to the other and undo things. The logical order is very important in this case. Higher level has a couple more ideas. There's a direct proof, a direct way of showing that the truth of a given statement by constructing a series of reasoned connected established facts. You don't need to say what these are, these axiom, theorems, definitions. We can kind of explain them and work through them. If you do take an analysis course when you get to university, you may need to write these down or will need to write down what these are, the names, commutative properties, etc. But for now, just using slow step-by-step patterns and really showing each individual step will be enough. At the end of these, you should write a concluding statement, whether it's a sentence or that the left-hand side is equivalent to the right-hand side, or QED, this Latin phrase that I'm not going to try to pronounce, what was to be demonstrated, and kind of do the thinking for the reader that the proof is then done and you have shown equivalency or the identity to be true, for example. So here's a nice simple example. There are a couple ways I could start here and then work all the way through individual steps to get to this. I could also set up a left-hand side, right-hand side proof. You can either set it up as a column or just, I'm going to start with the left-hand side, 26 over 30, pretty simple. And then you could say, well, on the right-hand side, you can keep working through logical steps here. Okay. And then you could say, well, that's the same as 2/3. This would be if you had to write it out by the fact that you are multiplying by 1. So there's an identity in the multiplicative identity. But again, you don't need to write any of this out. So we're just multiplying by 1 here. These are basic ideas, multiplying and adding fractions together. And because you have that the left-hand side is equivalent to the right-hand side, then you have shown that this is true. Okay, we have proven 26 over 30 is equal to 2/3 plus 1/5. You could also just kind of work through the steps of this. Could also take a left-hand side, right-hand side approach in this case. You can't start here and work backwards. It is sometimes arbitrary, but sometimes it's significantly easier to go in one way than another. But I'm just going to start here and keep writing logical statements and steps, not needing to justify any of this. Expanding this though, 3x, 6, 12. Okay, you could have that's been expanded, and then you can simplify this. And then you can factor out, so 3x, 4 plus 3x, and that is the same as, like if you were again writing this, you would have to say that this is like the commutative property of addition, but you don't have to. So you could say now QED, with that has been demonstrated that we have this proof. This is an identity because it is true for all values of x. You will see, especially at higher level, a lot of symbols. These are just a couple of them, is an element of, a lot of times you've seen these already in class that I'm using it. The set of natural numbers, I know you've seen this a lot. Integers, okay, if you speak German, like many of you, Zahl, it's a number. Sometimes you'll see it with the plus sign meaning positive integers. You have the rational numbers, which is relatively easy to recognize as quotient, where you have this division, real numbers. And not that long, we'll get up to complex and imaginary numbers. You may see is divisible by, hopes if I write that correctly. Sometimes it's just a vertical line, like A divides B. What you'll often see, though, is you'll see that if you say, example, like some number is divisible by 2, you would say that that number, for example, is equal to 2 times an integer, where k is an integer, means 2 divides it. So you may often see it written like this. This is really useful for doing math on it. If it's even, so some number is even, that means there's an integer that multiplied by 2 to give you this, or odd. Well, you can write it in a few different ways. You could say, well, it's an even number plus 1 or minus 1. If you have consecutive ones, you could call them 2k plus 2, or 2 times k plus 1 would be the next one. So there are many different ways you may have to represent things. Is rational, if you want this number to be rational, then it has to be 2 integers divided by each other, and they're coprime because they've been reduced all the way, which means there's no other factor that you can kind of divide out by. I wouldn't write it as 3/6. That wouldn't be how we'd write this number. We'd write that as 1/2, so they're coprime. You may also see, for example, this, which is for all elements in something. You may see something like this. There exists, but we can also write out the words for those. It's not a problem here. You will see them a lot. You already have seen a lot of them, and we can use them going forward. Here's more of a direct proof. Show that the sum of the digits is show that if the sum of the digits of a 3-digit number is divisible by 9, then the 3-digit number is also divisible by 9. And we're going to have to find a few ways to write these things mathematically. I'm going to find my notes so that I don't take too long to do this. So we have some kind of 3-digit number here. Let's say this number is A2, A1, A0. But we need to find some way to represent the digits and these numbers in the same kind of way. So like A2 is some digit, but it's in the 100s place. So a better way to write this would be that we have, this is some integer times 100 because it's in the 100s place. A1 is some digit times 10, could be different. And this ones place is just some other digit, where these P, Q, and R, they are an integer or a natural number. And P can't be 0 because we wouldn't then really have a 3-digit number. What I know about that also is that the sum of these digits, so P plus Q plus R, is equal to an integer times 9 because it says it's divisible by 9. So K is an element of the natural numbers, and if the integers, and if I multiply that by 9, then I get the sum that I get something that is divisible by 9. So this is my assumption. I know N can also be written as 100P plus 10Q plus R, because this is the way I'm breaking down this number, A2, A1, and A0. What I can do is use this and work through the properties of mathematics, divisibility, etc., to prove that this 3-digit number is also divisible by 9. So knowing this, what I'm going to do is I'm going to take that and keep writing logical steps. I could say R, for example, is equal to 9K minus P minus Q. And then I could substitute that in. So N is 100P plus 10Q. This is by the first statement where we've kind of defined our number, plus R, which is 9K minus P minus Q. And if you keep going and following these logical steps, then you have, this is equal to 99P plus 9Q plus 9K, which is, I can factor that out, 11P plus 1Q plus K. But because we have said that P, Q, and K are all integers, they're all elements of the integers, then 9, or I can do the next thing. So 11P plus Q plus K is also an element of the integer, is an integer. They're not going to be too picky about what this looks like in terms of formality. So n is divisible by 9 because it's 9 times an integer. N is equal to, how about it, times some integer. It doesn't matter what I call it. Let's call this c, where c is an element of the integers. So n is divisible by 9. Okay, and with that, we have proven it.